idea. Let's go over here. So axial stress. So obviously it has a couple of two words, axial. And what we mean by that is that there's a force, external force. We do have to keep in mind the difference between external and internal forces. The external forces are all the things that are, pushing and pulling on the object, whatever it is. And the internal forces are the ones that are inside the object, making it stretch and bend and twist and flex and all that kind of stuff. So axial means that there's some kind of force applied along, and not every object is going to have a longitudinal axis exactly, but we're going to call it a longitudinal axis. And we'll start out with stuff that has a pretty obvious longitudinal axis on it. But you don't have to have a longitudinal axis to have an axial force. But that's what we're going to kind of assume, is that there's some line that looks like a longitudinal axis for the parts that we're talking about. And then we're talking about stress. So stress, we're going to say that that's the intensity of these internal forces. So whatever is happening on the inside of the object, we're kind of, how intense is that? And if it's too intense, then things start to stretch. And if it's even more intense, then things start to break. So another word that we might use interchangeably with axial stress is normal stress. And in this case, what we're saying is that the stress, this intensity of the internal forces is on a plane, like a geometric plane, that's normal, so it's normal stress, to whatever the force is that we're dealing with. And in this case, normal means perpendicular. And the general idea is that you take and calculate this normal stress or this axial stress, and you compare it to the material strength, and that'll tell you a factor of safety. And if your factor of safety is greater than 1, or if it is 1 or greater, then you're okay, at least under those exact circumstances where you calculated that. And if it's less than 1, then you probably are going to have some chance of failure in your part. And failure might just mean that it stretched out some. It might not necessarily mean that it broke, but a lot of machines and a lot of buildings and things, if they stretch too much, then that's also failure, whether or not they catastrophically busted into pieces or whatever. So the general equation here is sigma. So this is my Greek letter sigma. I guess it's capital G for Greek. Equals F over A. So it's a super simple equation, and technically we're calculating an average stress. So there's a peak stress, some larger stress in our part, usually wherever the load was applied or around some really sharp corners, things like that. We're ignoring those for now, and we're kind of doing this average stress. So for instance, if I thought that I was dealing with a plate, and by plate I just mean a metal bar, and it's got some hole in it, and I put some kind of axial force here, then there are average stresses that are the one that I'm calculating. They're going to be over in this area, but there's these really high stresses. If I really did apply a point load like I've drawn here, there's a lot of stress right there, and it kind of evens out or averages out over space. And then around this hole here, there's some peak stresses. Those are not the ones I'm calculating. I'm calculating kind of in the bulk material where they're averaged out. and it's kind of this average thing. So just force F in my equation over here. This is the internal force. So I have to actually mentally or draw a picture and cut this plate that I drew. I have to cut it open and see what force is on the inside of it. This area is a cross-sectional area. And then sigma is the axial stress or the normal stress, whichever you want to call it at the time. So we're doing the average for now. At the very end of the quarter, we'll do a little bit of calculations on these peak stresses, these maximum stresses. There's two basic ways you can do that. Either you can put it into some simulator like SolidWorks and have it go through and iteratively solve what these maximum stresses might be. There's even a way to use these factors, coefficients that multiply the stress to calculate these peak stresses. So they are a thing, and obviously if you don't design for the worst case scenario, the peak stresses, then you may under-design your part. But for now, we're going to calculate these average stresses, so the stresses in the bulk material. Let's see. Let's do a simple example of this. I think did I already draw the picture? Maybe I did, I don't remember. There we go. Oh, well, first let's watch this little video. So this is a piece of rebar. It's kind of dark on the screen there. If you watch it on the video later, it'll be brighter. But this is a tensile testing machine. In the center, you can kind of see a darker bar there. That's the piece that's being tested. All this on the outside is just part of the machine. Let's see if it'll play. I did not bother to check to see if I was connected to the internet or not. Oh, good look. You can get a little sound. So what's happening is off the top of the screen, there's a crosshead that's moving up really slow, like ½ inch per minute or something. I don't know. And so that's the kind of failure we're talking about here. And they just play it again at a slow speed. But we're pulling something apart in pure axial, like stretching something out. We also, this equation, sigma equals F over A, it would apply if we were pushing on things. As far as calculating the stress, the failure would look differently when you push on things. But that video it's actually a tensile test. So one of the things you do with that video is collect data on how strong the materials you're dealing with are. You'll do that is lab 1, basically, not with that size material, because that was, I don't know, 10,000 pounds or 15,000 pounds to pull it apart. You're going to do on a much smaller piece, and it'll be 100 pounds to pull it apart, something like that. And it'll be wood. It won't be a piece of metal like that. So that's the kind of thing we're talking about. In fact, why don't we do this? Let's look at these. So these are two little bars. One of them is clearly has a longitudinal axis here and 10 pounds applied on either end of this bar. And what I want to show here is the idea of the internal force. Let's get some more room in here. So this one is super simple, but it's best to learn on the simple things and do all the procedure, even though it seems kind of silly to do, because they get more complicated. And if you can't do the simple ones, then you'll have a really hard time with the complicated ones. So the thorough procedure here would be, if I want to solve for this equation, sigma equals F, sometimes this F will be written as a P, the letter P, but here I'm just going to use F over A. Then I need F, and remember I need the internal force. I have these two 10-pound external forces, but I need what's going on the inside of the bar. And then A, I need the cross-sectional area that this force is applied to. So the first thing that goes wrong with some people is they look at this bar and they want to calculate the stress in it, and they don't think about drawing and looking at the internal forces. They just say, oh, well, it's got 20 pounds on it. So it's 10 pulling one way and 10 pulling the other way. But that's not the internal force. The internal force is only 10 pounds. It's not 20. And it is obvious when you actually take your bar here, make some line that you're going to cut through, and then draw it. It doesn't matter which, let's draw this side. And then we cut, you know, on this little surface right here. So we cut that open. So the internal force is on that little blue area. So here's the external 10-pound force. And then for this piece to be in equilibrium, it would need 10 pounds going this way. And so the internal force is only 10 pounds. And so then you go over here, F equals 10 pounds. A, we didn't give it any dimensions. Let's just say it has an area of 0.25 square inches. However, you know, it's a circle. We calculated the area and figured it out. So let's see, then you just take 10. Let's see, 10, get my calculator going, divided by 0.25, 40. And then the units on this are pounds in the numerator and square inches in the denominator. So normally, pounds per square inch, instead of you can write it this way, pounds in the numerator, inches squared in the denominator, but normally you write 40 psi. And then you have to determine, is that a lot or not? And so that depends on the material. 40 psi for some materials is breaking. 40 psi for other materials is it's not even a thing. You know, it takes thousands or tens of thousands of psi to break the material. So you have to know something about the material to tell if it stretched or broke or anything like that. In general, 40 psi is pretty low. So any metals, that number before it starts to even stretch is going to be, you know, at least 25,000 psi or more than that for most materials, most metals. We'll get into that side of things later if 40 is a lot, but so that 0.25, was that already given? I just totally made that up. Normally you would go and calculate the area. We'll do some calculating of the area in a minute. I just didn't want to bother calculating the area. All right, this one, a little bit more tricky. So this one, I've got, first of all, I've got an X in here. I've got two 5-pound loads and a 10-pound load. So again, we're assuming that everything in this course is statically equalized, so it's in static equilibrium. So that means I should be able to solve for X. And in general, it looks like these forces are all in the X direction. So I know that summation, oops, I want to write that in green. Summation of forces in the X direction should equal 0 if this little part is supposed to be in static equilibrium. And I have 5 pounds plus 5 pounds plus 10 pounds minus X should equal 0. Therefore, X must equal 20 pounds. So X over here looks like it's supposed to be 20 pounds. Now, there's two sections to this one, so I might want to do two free body diagrams. You know, one free body diagram where I come in and maybe cut that little piece off and look and see what the internal force there is. It looks like that one would have 20 pounds over here, so the internal force on this one should be 20 pounds. And then if I look at this other piece, you know, cut it off over here, then here's that little area. I couldn't really see it over on that one. 10 pounds external force applied to it. So there must be 10 pounds right here. If I wanted to draw the middle piece, I could do that too. Normally you only need to draw one piece of it, but it looks like in this little case, the left-hand side, so let's make it this way. The highlighted one right here is the one that we would need to design for, assuming they're both the same material, same diameter, that kind of thing. That one on the left is going to have twice the internal force as the one on the right, little bar on the right. It doesn't intuitively look that way though, because you've got this 5 pounds pushing on the piece and you got 10 pounds pulling on it, but when you draw the free body diagrams, you can see that, oh, well, there's only 10 pounds of internal force on that left-hand side, and there's 20 pounds on the right, or well, 10 pounds on the right-hand side, 20 pounds on the left-hand side. One thing I'm doing when I'm drawing these little green wavy lines to show where I'm cutting is I'm kind of cutting in the middle of sections, because if I do something like this, I try to cut right through the edge here, it gets a little confusing to me whether or not I include that hub, whatever it might be. So whenever you identify a section, go to the center of it and draw your little free body diagram there so that you're not confused if the force is applied to it or not. Because it's pretty obvious when you are in the middle whether or not to put those 5 pounds on the free body diagram or not. Let's just draw, let's copy this thing. And, whoops, paste it. I don't want that on there, I need some room. Oh, that's the YouTube video that goes with lecture 2. Not what I wanted. I want this. Well, let's just draw it. So let's assume that I did this. I cut it right there, and I want to draw the left-hand side, just for completeness sake. And then it comes out, and I kind of cut it right there. So here I've got 20 pounds. This is external. There's 5 pounds. One little note on these two 5-pound forces, sometimes it's confusing whether or not there's 2 of them or there's one of them that's spread apart. So what I'm going to do is, if there are 2 individual 5-pound forces here, then I will draw 2 arrows and 2 5s. If there are only one of these that's spread over this whole hub, then they'll be connected together somehow. And there might be a whole bunch of them, and there'd only be one 5-pound label on them. So this is representing 2 separate 5-pound forces. The reason we're doing 2 is if I only did 1, then now this 5 pounds is not on the same axis as the 20 pounds, and I get a thing that we're not ready for yet. So I get some flexing of the shaft that I'm not ready for yet. So if I do it this way, that flexing bending goes away because it's canceled out. So that's why there's 2 separate ones. Or sometimes there's one that's distributed across the whole thing. It's just to keep us in this idea of axial forces. So my internal force, I don't really know, is it going this way or what? I don't know. So I just pick one direction. I chose, again, I'm assuming X is positive when it goes to the right and Y is positive when it goes up. And then write the summation of forces, and X equals 0. And I've got 5 pounds plus 5 pounds. I drew it going positive, so plus F. And then the 20 pounds is going to the negative direction, so minus 20. Those have to add to 0. And then I will get, therefore, F equals, and I get 10 pounds. And it is a positive number here. So the 10 pounds being positive, positive answer in this case, means that the arrow I drew for F is going the right way, the correct way. So I chose wisely when I drew F going to the right. And I didn't really choose it going to the right or left. Remember, when I'm talking about these stresses, that I have axial stresses are divided into tensile stresses, so pulling things apart, and compressive stresses, pushing them together. And when the arrow points away from the body, so I drew F going away from the little free body I drew, then I am indicating that I think that piece is in tension. So that's a thing to remember. Arrows pointing away from free body indicate tension. So if I had solved this thing and F came out to be negative, that would mean that I should have drawn that arrow pointing the opposite direction of what I drew. And so that would point it towards the body, which would mean it was compression in that little section of the shaft or whatever this thing is. So keep those things in mind. Tension and compression, they are going to be big concepts. In general, metals don't behave any different in tension or compression. They're pretty much the same, but other materials like concrete behave very differently in tension and compression. So it is important generally in metals, which is most of what this course will have is metals and a little bit of wood material every now and then mixed in. Generally, metals are the same in tension and compression as far as strength goes. But you still need to know. Another reason you might need to know is this. So let's say you have a bar of some kind, but it's really thin. So like this. And you put it in, this would be tension. So sigma equals F over A, that's fine. But the same bar, and you put it in compression, even if it's metal. So now, even if this was a metal bar, but it's really that size, really long compared to how wide it is, and then the equation, sigma equals F over A, is still true as far as compressive stress goes, but the failure mode is way more likely to be buckling. So if you've ever taken like a yardstick or whatever, but a yardstick, something long, or a dowel rod and pushed on it, then it probably didn't like crumble under you pushing on it, but it bowed out. And so that's a different thing. Another reason to know tension from compression is because different failure modes occur under tension and compression. So it is important to get these signs correct, not just for the math to work out, but the actual failure mode might change when it's tension versus compression. All right, let's look at this guy. So here's our little isometric grid again, and we've used it to draw a plate, so a little metal plate. It has a hole in it, and I've got some forces. Let's see, maybe let's make a more force than last time. Let's do 5,000 pounds. And if I have 5,000 pounds pulling the plate kind of this direction, for it to be in static equilibrium, I need another 5,000 pounds over here. Now it's in static equilibrium, and it won't, move, accelerate somewhere. I've got some dimensions. Let's assume these are all 1 inch. It doesn't have units on them, but let's assume that it looks like this distance is 1 inch. All right, and I want to calculate the stress in this, the axial stress in this plate that I've drilled a hole in. So there's a couple of things I can do. First, I'm going to ignore the locations where the stress is concentrated. So, the way I drew it here, there's a location right in here and one on the other end that has a really high stress because I've got this point load. It's like a hook or something there that where all the load, this 5,000 pounds, is applied. So there's going to be a really high stress right there. And anytime you change dimensions, so like I was at 3 inches wide, and then all of a sudden I am at 2 inches wide because I drilled a hole in the thing. Anytime you change dimensions like that, there are stress concentrations. We're going to ignore those two. And what I'm left with is this idea of the average stress. So I also generally want to know where the stress is highest without thinking of the stress concentrations, but thinking of just the geometry. Where is there the highest stress going to be? And if I look at the equation, sigma equals force over area. In order for sigma to get larger, either F has to increase, so the F goes up, then sigma goes up. Obviously, if you put more force, if I made 5,000 pounds equal to 10,000 pounds, then I have increased the stress. Also, as A, the area goes down, sigma goes up. So the more I concentrate the 5,000 pounds into a smaller and smaller area, then that also increases more stress, or increases the stress on that area. So since this part has a hole drilled in it, it is going to have the largest stress if I do my little free body diagram cut across here. So if I take this plane and cut it apart right there, that's going to have the smallest area here. So I will probably, let's draw that, let's see, where would be a good spot? Let's draw it just up here in the top corner. So I made this 3, I have to erase that. So 1, 2, 3, and then I made it 5, and I put this hole, I didn't actually say where the hole is, it's in the middle. So 1, 2.5, 2.5, and it's a 1/2 inch thick. And then there's this hole right here. And that's my, if it broke really cleanly, and I'm assuming when I'm calculating these stresses, I'm assuming that everything snaps like perfectly in half on these planes and everything. In real life, they're all jagged and everything. We're not in this class worried about the roughness of stuff. We're assuming everything's perfect. So these little shaded areas, those are the areas that support my load. So I've got, let's make it red. Got 5,000 pounds of external force. And then I'm going to assume that half of it ends up on either one of these little surfaces around the hole. So 2,500 pounds gets split up there, and 2,500 pounds on that side. And those areas are the ones that I want to use as the area that goes into my stress equation. And notice it's a normal stress because this 2,500 pound force is perpendicular to the little blue area that the stress is on, so that makes it a normal force. It's axial because if I thought about a longitudinal axis, it would be kind of like that direction, right? And all of these forces are more or less balanced around that longitudinal axis, so axial stress. And to calculate it, I would just need to figure out the force that goes into this equation over here and the area that goes into it. So sigma equals the force is, and I can do this one of two ways. I could look at one area, and one of those areas has 2,500 pounds on it, or I can combine them together. I think I'll combine them together. So I have two 2,500 pound forces, and I have two areas that are, this dimension is 1/2 inch, and these other dimensions are hard to show on there, but they're each 1 inch. I'll put one of them on there, kind of getting cluttery. 1 inch, if I could write small. So I have two areas that are each 1 inch by 0.5 inches. So my units look like they'll work out. I have pounds in the numerator and I have square inches in the denominator. And you can see from here that the 2's just cancel out. So it's going to be the same as calculating just one of them. And it would be 2,500, well, divided by 0.5. So 5,000 PSI. And that's getting, now I have several thousand PSI. So I would need to go and reference some material properties to see if that's a dangerous amount of stress or not. Notice that the 5,000 PSI, I don't even have to know the material here. This thing could be styrofoam, or it could be concrete, or it could be aluminum, or it could be steel, or it could be titanium, and they all have 5,000 PSI of stress in there. Whether or not 5,000 is a lot depends on what the actual material is. And if I put 5,000 PSI and it was styrofoam, it probably would break and never develop that much stress, but that's not quite the point yet. So I think, let's go back to Moodle here for a second. If we look in General Resources and this folder, Reference Materials, here are material properties. There's a material properties PDF that will have, let's open it. So if you have your book, it's also page 704 in your book, and that one's page 705. Let's zoom in on it a little bit though. All right, so across the top up here, I have different things. I have specific weight, so that's like the density. So if I had the volume of it, I could figure out how much it weighed, which we do have the volume, we can calculate it. So we can figure out how much this little piece weighs. Then I've got these two broad categories, one of them elastic strength with 3 columns under it, and one of them ultimate strength with 3 columns under it. Those 3 columns are tension, compression, and shear. So this one that I'm dealing with, the arrows are pointing away from the little areas that I was using to calculate. So that means that's a tensile stress and a tensile force. So this is tensile stress. That means that I would reference the tension column under either elastic strength or, this one or that one. So the difference is one of these is elastic, one of them's ultimate, and they kind of are very well named. Ultimate kind of sounds like what it would do is you cannot put more than that. Any more than whatever numbers in that column is going to lead to fracture. The elastic one's not quite as obvious, but still, if you think about elastic and it's stretchy and it snaps back to its shape, that's what they're talking about. If you put more than this number, then it will not go back to its original shape. If you put less than this number, then it might stretch a little bit, but it'll go back to its original shape. And then you've got all these materials, so wrought iron and structural steel and all these different things. A lot of times we just use this generic structural steel. It's not even a real thing, but this would be kind of the steel you might think of some buildings, beams being made out of or whatever. It's kind of generic. And normally when you're building parts, you don't want them to what's called yield. Yielding means that you went above the elastic strength, means that it's stretched to a point that it will never go back to the original shape. Sometimes you do that on purpose before you put the thing into service, and you'll learn about that in a materials class and more in this class too. But normally you're designing against this one. So this 36, and the units on it are weird, 36 KSI. So KSI is not, doesn't, it is what it sounds like it would be. So it takes the K from the metric system, and then the SI part from the PSI, and so a KSI equals 1,000 PSI. So this number in our chart says that the elastic strength of this generic steel is 36,000 PSI. So if I get more than 36,000 PSI for this number, then I have permanently changed the shape of this plate that has a hole in it. And you generally don't want to do that. Other numbers in here, you know, there's some of these stainless go up to 165. There's some wood material down here that's more in the, you know, 4,000, 8,000 number. And they're all kind of over the place. So you do have to look and see what material are you dealing with to see if the number you calculated meant that it was going to break, or if it was going to fail or yield, or is it going to do anything. So we would write down that sigma, and normally we write a Y here. So this would be the yield strength. And then your book uses the term elastic. So yield or elastic strength equals, it was 36 KSI that was for structural steel. We have 5,000 PSI, which is 5 KSI, so we're well under the point for this thing to start stretching permanently. So 5,000 pounds on this little plate should be okay. If we did the free body diagram kind of in this area over here, you know, kind of over here, then our area would be even larger. It would be 3 inches times 1/2 inch high. So our stress would be smaller. We'd have the same 5,000 pounds on that area, but we'd have a larger area to spread it out over, so the stress would be lower. Remember, stress is the intensity. So as you get the area smaller and smaller, more concentrated, then you get higher and higher stresses. That green, that second plane that I drew, so this one, it is kind of close to the application of the point load, so it might be a place where you do get a little bit of the effect of the, you know, this effect where I've got really high stresses out there. So I might have some higher stresses in that area, but again, we're not going to calculate or deal with those until the very end of this quarter, and we'll do that later on. All right, very good with that. Does that make sense? Most of what we're going to do from here on out is built on this kind of idea. Finding a little area, figuring out what forces applied on that area, and calculating the stress. And then checking in some chart somewhere if that's a lot of stress or not. All right, let's see if I want to go on to this next picture. I think so. All right, so this one, here the force is pushing on this thing, and this like blob behind it, whenever you see these, you know, that kind of cross-hatching, that normally, and for me it always means this pretty much, but normally that just means that you're not considering that. That's kind of indestructible, immovable wall or whatever. So it is not part of the problem. It is just there to show that it's way stronger than whatever it is you're dealing with, and you can assume that it's not going to deform or break or anything like that. So it's kind of indestructible or something. In this case, it looks like a wall. And so it's just there, and it's blobby on purpose because you don't need to know anything about it. Here, we've got what's called a bearing stress. Well, it'll be okay. So this one I would call bearing stress. And sometimes you might call it a contact stress, would also make sense. So you have two objects that are pushing on one another. Here we've got this little square plate that's pushing on a wall. And so whenever I've got two areas in contact, then they develop a stress between them. And if that stress gets to be too large, then one of them could fail. So normally the failure here is not like fracture, well, it could be, but there could be some deformation or that kind of things. There could be a fracture type failure also. We're not too concerned of the mode of failure right now, just that there could be failure. So how this works is a lot of times, move this one out of the way. A lot of times you'll have sigma B, and so the B is for bearing, but the equation looks exactly the same. So this is bearing stress. And we need a force on here, I guess. So let's make this 8,000 pounds. And the area, let's make, looks like this looks like 3 inches. And let's put this one over here. I think that one's also 3. All right. So the area in bearing stress is the common area between the two parts. So wherever they overlap at. So in this case, it would be this 3 inch by 3 inch square would be the bearing surface. So area equals bearing surface. And that is the contact. Sometimes you'll see contact patch area, but it's basically just wherever the two parts overlap. Obviously the wall is way bigger than this little 3 by 3 plate, so the contact area in this case is 3 by 3. And then you go in force. Again, we're assuming that the force is evenly distributed. It could be, you know, if this plate is thin enough, then it could be that you get a little bit of stress concentrated right, you know, around this area here, since I've got this smaller rod that's pushing on the wall or on the plate, which is on the wall. But we're going to, again, assume that everything is taken into account in a way that we don't have to deal with stress concentrations. So I would just say sigma B equals the force, the 8,000 pounds, and it's spread out over this 3 by 3 inch area. And so again, my units work out. I have 8,000 pounds over 9 square inches, and I get 888 point, a whole bunch of 8s. And thinking back to our chart a minute ago, that's a pretty small stress for most materials. Obviously, we want to know, is this strong enough? Is the plate strong enough for that? And is the wall strong enough? In this one, we're kind of assuming the wall has this indestructible characteristic, so we don't have to worry about the wall, but maybe the plate itself is too fragile to deal with 900 psi. Although most materials, 900 psi is not a problem. So that's a bearing stress. There's an odd bearing stress that we might have to deal with here. So here I've got a plate that's got a hole in it. Again, usually those holes are there because there's some sort of pin or bolt or rivet or something in that hole. And what can happen here is, actually, let's take one of these forces off. Let me draw a side view of what might be going on here. Let's say that this is the side view of our same little plate we've got here. And there's a hole somewhere in here. And let's make this thing attached to a immovable shelf. And maybe there's a bolt in here, really big bolt for what we've got going on, but so there's some bolt in that hole, and I'm pulling this way. So what ends up happening, if there's a bolt in that hole, And the bolt is, again, indestructible. We're not worried about it right now. I am forcing only half of this hole to support all this force. Stop. You know, kind of this half of the hole is supporting the force. Let's make this, what number? Let's make it 10,000 pounds. So all of this added together over here is 10,000 pounds. Now the problem with it is, if we look at the top view, let's put a circle in there. These 10,000 pound force that I've got, they're not evenly distributed. It's largest in the middle, and then it kind of tapers off as we get closer to the edges. And right here, it's basically zero. Might actually show up better if I drew radial lines, but we'll do it this way. So largest in the middle, and then it tapers off towards the edges. So to deal with that, we still want to do the same idea where we have a force, 10,000 pounds, that's spread out over an area. But since it's unevenly distributed on this area, what we're going to do, instead of just doing sigma divided by A and A being the curved inside area of that hole, we're going to do what's called a projected area. So we're going to use the idea of projected area. And what that means is, let's do this. So we have to look inside it to see what's going on. So instead of using this area, which we could calculate that area, it's just a half of a circumference of this hole and however thick the plate is, but the forces on that area are not evenly distributed. We're going to project that curved area onto a flat plane like this. So we're going to project the curved surface onto that flat area. And that will be the area that goes into sigma bearing equals F over A. Since I drew this free body diagram, I would have these forces. I put 10,000 pounds total, so I would assume that they get divided equally. So 5,000 pounds there, 5,000 pounds there, and then on this projected area would be the whole 10,000 pounds. And so I would have the forces 10,000 pounds. And the area is, I don't think I gave this thing any dimensions. It's a 1/2 inch thick. So that's that dimension. And let's make this hole looks like 2 inches. So put it over here. Remember, that's the little symbol for a diameter, so it's got a 2-inch diameter. Oh, well, yeah, that's just 1 in the denominator, isn't it? So 10,000 psi. What this is telling us is basically, go back to our original deal here, if I pull hard enough over here with the 10,000 pounds, then it's not talking about the whole breaking, but it's kind of talking about the whole deforming, you know, like this. Not this extreme, but the whole could, deform. And so it's not necessarily that the thing's going to fracture and pull apart. That's a different thing. But if the hole gets too oblong, then things will move around and it could lead to other types of failure. So that's the thing that we're trying to guard against, is this hole getting oblong shape. All right. Are we good with all of these axial stresses? All right. Then let's add the idea of shear stress. So shear stress, let's say that I've got these two little plates and they're overlapping, but I'm not pushing them together. Let's say that they're glued together. So I've got some glue on this surface. You know, where they overlap at. So if I were to draw a free body diagram, it would be kind of hard to draw, but maybe it would look like this. Let's look at the bottom plate and we can maybe figure out a free body diagram. Let's put it over here. I made it 6. Oh, that's going to overlap. Let's move it over some. Go out there. And it goes down to here. Oop. There. All right, so the little area of glue is back here. So the glue is what's holding them together, the adhesive or whatever it is. But the force that's trying to pull it apart is this way. Well, kind of that way. That way. Let's make it 7,000 pounds. And since the glue is what's trying to hold it together, I have to draw the force maybe something like this. I'm only going to put half an arrowhead on there because this is a different type of force. This is called, whoops, leave that. This is called a shear force. When we did the normal forces, normal stresses, the force and the area that it was acting on were perpendicular to one another. Here, this force is parallel to the area that it's acting on. And I didn't draw, you know, it's distributed over this whole green area. I just drew one arrow to represent the whole thing, but it's actually distributed over the whole green glue area. So since it's not perpendicular to this area, then I have to treat it a little bit differently. And the way I treat it differently is I drew only half an arrowhead and I called it a shear force. So shear forces don't create axial stresses. Can I not zoom? There we go. They create shear stresses. So shear force is not perpendicular to area of stress, the area that you're dealing with right now. And shear forces create shear stresses. And that's important because it's a different strength. Shear force creates shear stress. And the equation is the exact same form, but we use different variables. So now we have tau. So this is Greek tau. And it's shear stress. Equals, instead of F, we're going to have V, but it's just going to be shear force. And then A is the area, in this case, the area of the glue, so the area that the shear force acts on. And it doesn't have to be glue. You can have shear forces in bolts and rivets and things like that. You can have shear forces in these plates if we arrange the forces differently. We'll look at some other samples here in a second. But for now, let's calculate this. So I've got 7,000 pounds of shear force acting on an area of glue that is 5 inches. I'm getting that from over here. 5 inches by 6 inches. Going back to my original picture there. So there's actually quite a bit of area for this to work on, which will reduce the stress, which is a good thing. So 7,000 divided by 5 times 6, 233 psi. Now this is a shear stress though, so that's the important part. So you have to compare this to a shear strength. Not tensile or compressive strength. So in our little chart, see if I can, there it is. Let's get rid of those. Notice under both of the elastic column and the ultimate strength, I have shear columns. Now a lot of them are empty, there's nothing in there. That doesn't mean it doesn't have shear strength. It means you got to go down to the bottom of the chart and let's see. For ductile metals, so that's most metals like aluminum and steel and things like that, not metals like cast iron, but ductile, not brittle. It is customary to assume the properties in compression have the same values as those in tension, so that's why a lot of these just say B for compressive strength. See what else we have down here. Something for rotating beam. So this one doesn't specifically give us what to put in here, and that means that we have to have an equation that gives us a number for shear strength. And there's a lot of different ones that we can use based on different failure theories, and depending on what major you are and what field you go into, a different equation will be more relevant, but a good one to use. So a good one that is kind of generic is that whatever you have in tensile, you just divide it by 2. So tension divided by 2 will give you the shear strength. And now that's not, there are better equations in other situations, but in this class, the one we're going to use is we're just going to take the tensile strength and divide it by 2. Some of these materials have, they have a number listed and you use that number, but a lot of them don't have a number listed. So if they don't have a number for shear, then you just take the tensile number and divide it by 2. So same thing over in the ultimate strength column, for these numbers, take this tension and divide by 2. So if we were back to our structural steel, it has 36,000 psi tensile elastic strength. The number that I would use here would be 36 divided by 2, so 18 ksi for shear. So that's why it's important to be able to tell shear from tension and compression, because in general, the materials that we're going to deal with are half as strong in shear as they are in tension and compression. So if you calculate this number, it was a really low number, but 233 psi, and you compare it to the tensile or even the compressive strength, then you're not comparing it to the right thing. You might design the part wrong. So you do need to be able to tell the difference between shear stresses and axial stresses. And you tell the difference by, is the force that created that stress perpendicular to the area the stress is on or not? And if it is perpendicular, then it's a tensile or compressive. If it's not perpendicular, and in our class, it's pretty much always going to be parallel. If it's parallel, then it's a shear stress, and you can't interchange them. Even though they're equations, you know, they're basically the same equation. Stress equals force divided by area. It's the same equation in both of them. Just different stress, different force. Here's two different ways that shear stress might show up. Let's go back to this idea of the bolted down plate. So let's look at that side view of this thing. And it won't necessarily always be bolted. Sometimes you'll see this called pinned, and that just means that there's some kind of bolt or pin or rivet or dowel rod or something that's holding things down. So pinned is kind of a more generic term. So here it is. We're not going to draw the whole thing. We're just going to draw the plate. And here's a little hole. Here's the force. Let's go back to 5,000 pounds on it. And then inside this is some kind of pin, whether it's a bolt or a rivet or whatever. It doesn't actually matter right now. But let's say there's a bolt. And it's in here. And it breaks right here. So basically, you know, this part goes that way. So what would have kept it from doing that is this little force right here. So that would be our shear force, V. And it looks like for this piece to not go to the left, not go flying off to the left, that V needs to equal 5,000 pounds. Otherwise, it's not in equilibrium. So the question is, can the bolt handle 5,000 pounds of force right there? That's the question that we need to answer. And that kind of depends on what the bolt's made out of. Let's assume that it's that generic steel thing that we've been looking at. And let's look at how big this bolt is. So in this case, how about we design the bolt? So let's do this same equation that we've been doing. Tau equals V over A, but let's make A the thing we solve for. So we figure out how much area of bolt we need in order to make this not break. In fact, let's make it not yield. So we need to go back to our little chart. If we're using the structural steel material, then again, there's no shear strength listed. So that means we have to take half of the tensile strength. We're going to look at elastic because that means that we don't even want it to deform permanently. The ultimate would mean we don't want it to fracture and come off of there. In general, if things start to deform, then they will eventually fail anyway, so we're just going to not even have them deform. So we would need this no more than 36,000 divided by 2 KSI of shear stress in our bolt. So tau max, the maximum amount of shear stress we can have is 36,000 PSI divided by 2. So 18,000 PSI. V, the shear force we need to support at our free body diagram, says it's 5,000 pounds. So we can just put 18,000 PSI equals 5,000 pounds over A. And A equals, let's see, 0.278, we'll say, square inches. Now, normally you don't design bolts based on, like, you don't name them based on their area. So we would more than likely want to know a diameter here. So area equals pi d squared over 4. That's just the equation, or pi r squared if you want to use radius. So let's see. Area equals 0.278 inches squared times 4 divided by pi. And then the square root of that equals the diameter. So it says that we need a diameter of 0.595 inches. Now, normally bolts do not come in 0.595 inch increments, so we'd probably have to round that up to the next logical size. We're not worried about actually designing as far as, well, what bolt is the next size up or whatever, and go get all the diameters. If you're mechanical engineering or even civil, that will occur later on, but it's basically there are some sizes that are standard, some that are not standard, and normally you get the standard sizes. Now, what this didn't do is we're at that 0.595. If we went and got that exact bolt diameter, then we have no room for error. We have no room for maybe this thing to get heated up and change its properties, or get really cold and frozen and change its properties, or more than 5,000 pounds being applied to it, or, you know, we had no room for any kind of situation other than 5,000 pounds being applied to this perfectly round bolt in this perfectly round hole, and everything's perfect. Normally what you do is you include some kind of factor of safety. So you might say that, well, I want a factor of safety of 2, and you either go and double the force, so you make, I think it's supposed to handle 5,000 pounds, but I'm going to make it handle 10,000 pounds. I'll be twice as safe. Or another way to look at it is maybe you take the 18,000 PSI of strength and you say, well, let's imagine that it can only handle 9,000 PSI of strength. And so I'm going to make it half as weak, which will also double, you know, you have a factor of safety of 2. There's different ways to handle the factor of safety. Anytime in this class, you're either going to be calculating the factor of safety, like given all the scenario and the material properties, then what is the factor of safety? Or you'll just be given, design this part with a factor of safety of 2.3, you know, in some number. So you don't ever have to, you know, figure out what factor of safety to apply to something. Let's see. All right. So that's a little bit of shear stress. Here's one other one that's a little, it's related to the same thing though, but let's look at a top view of this bolt. I think it's the last one we'll do today. Put it over here. All right, let's say that we have plate. It's got a hole in it again. There's a bolt in there or a pin or whatever, and we're still pulling on it this way. And let's say that we made the bolt super strong, and the bolt is not our problem. Then we run into maybe the bearing stress being a problem. You know, it deforms the hole to where it's oblong, egg-shaped, and that's a problem. But let's say we are even more aggressive with our force. Maybe we put 20,000 pounds on here. And again, we have an indestructible bolt and everything else. What could happen is it could break, you know, right here and right here, and basically this piece could come out. So we'll draw that piece out. I'll put it kind of in 3D. So this is that piece. There's the top. And the red is this area, and the area on the left side of that that we can't see, it's on the other side of the part. So basically, you know, if there's a bolt in here, I'm pushing right here with 20,000 pounds. And I've got on this surface, maybe I should not have made those red, but there's a shear force here of 10,000 pounds. And then there's one on the other side that, you know, it's kind of back here, another 10,000 pounds. And those shear forces are parallel to the area. They're not perpendicular to it. So those are shear stresses on those two surfaces. So I need to do tau for shear stress equals V over A. And again, I can either look at these as a pair of 10,000 pounds and a pair of areas, or look at one of them. It doesn't really matter. I'll write it again as I have two 10,000 pound forces, and they are on two areas that are, we need some dimensions. So let's make the center of the hole to the end of the plate. Let's make that kind of looks like 2.5 inches there. And then the thickness of the plate I didn't even show. Let's make that over here 1/2 inch. So I have two areas that are each 2.5 inches long and 1/2 inch thick. And let's see what we get. And again, the twos just cancel each other out. So 8,000 PSI. And again, remember, if this is that generic steel, we had 18,000 was the point at which it started to permanently change its shape. So 8,000 is not too bad. We're still okay, but it's getting closer to having an issue. This is called Tearout because you're tearing out this little piece I colored yellow. This is called Tearout. It's also called punch out. Normally tear out is this scenario, and punch out is like you're punching like cookies. Like you got a cookie cutter and you're punching out cookies. It's that kind of thing. But they work the same way. Basically, you have an area that you need to shear and separate it from the other rest of the bulk material. So they're the same thing. They're both shear stresses. This one you normally call tear out. The cookie cutter type thing is normally called punch out. All right. I think that gets us the basics of shear stress and axial stress. Bearing stress is a part of axial stress. You've got some web work problems that are going to, re-emphasize each of these. Particularly, a lot of web work problems are going to look at this. They're going to call this a pin joint type thing. It's going to be two plates. We didn't do a lot of pieces all on the same plate, but I think there's one web work where you might calculate 3 or 4 of these modes of failure all on the same piece and figure out which one is the worst case, which is it's getting into interesting things.